All right, hi, this is your test review for Unit 4. So for number 1, we're going to look at this function on the interval from 2 to 4, and we're going to compare all the different Riemann sums. So what I would do is just draw a quick sketch of that, and we only want to draw the sketch from 2 to 4. We can draw the whole parabola if we want, though. It's going to go right 2 and up 4. So that's the center of it. It's going to be reflected, so it'll be upside down. If we plug in 3, we're going to get 3. And if we plug in 4, we're going to get 0. So it would look like this. This is the entire parabola. But we're only looking from 2 to 4. So we're only looking at this section right here. So the function is decreasing and it's concave down, it's bending downwards. So it's decreasing and it's concave down. So when we compare the left sum and the right sum, the left sum is going to be larger than the right because the function is decreasing. So the left side is higher up than the right side. The true area under the curve, that would be the actual definite integral, like the real answer, is going to be less than the left sum. The left sum is going to be an overestimate, the right sum is going to be an underestimate. And so the true area is going to be greater than the right sum. Again, the right sum would be an underestimate because the right side is lower down. And then we're going to do the same thing with ln of x. So ln of x has an asymptote at x equals 0. I'm going to do something like that. And we're looking from 1 to e. 1 is where the graph touches the x-axis. E is, about 2.7, so somewhere over here, and this is the part of the graph that we're looking at. So this graph is increasing for that section, actually it's increasing all the time, but increasing for that section and concave down. So again, we're going to compare these. The trapezoidal approximation compares how was the true answer. So since the graph is concave down, if you drew in trapezoids, they would be very slightly underneath. So the trapezoidal approximation is going to be less than the true actual area. The trapezoidal approximation is going to be greater than the left-hand sum. The left side is lower down than the right side, so the left side is going to be an underestimate. And the trapezoidal approximation is going to be a slight underestimate too, but it's closer to the true area. So trapezoidal is greater than the left-hand sum. All right, now we're comparing trapezoidal with the right-hand sum. Trapezoidal is going to be less than the right-hand sum. The right sum is going to be an overestimate. The right side is higher up than the left side. And then the left-hand sum is going to be less than the right-hand sum. And the left side is lower down than the right side because the graph is increasing. So we're just comparing all of it. So 3 and 4 are the same kind of question, just going backwards and forwards with this. We're going to write the Riemann sum for this definite integral. And then this is the Riemann sum. We're going to write the definite integral. So you can use these problems to kind of like help each other. It's going to be limit as n goes to infinity. And what that's saying is we want the number of sub-intervals to be infinite. You get a better approximation with more sub-intervals. So if you let it go to infinity, that's going to be the best approximation possible. And then you want to add up all of the rectangles. So that's what sigma means, sum. And we're going to start at 1, start at the beginning, 1 to n. And we're going to let n go to infinity. So the function is ln. And then inside of there, you put where you start, which in this case is 2, plus, and then it's delta x, it's the change. So since we go from 2 to 7, the change was 5. So it's going to be 5 over nk, or 5k over n, and then times that change. So times 5 over n. And again, you can use this format to kind of help you. We're going to do the same thing with this one, except go backwards. We want to write the definite integral. So this is where we start. So we're starting at 5. And the change, the delta x, is 3. And you can see that there. So 5 plus 3 would be 8. And the function is sine. So sine of x dx. All right, number 5, we're using our integral properties. We've got an integral from 2 to 7 is -5. Integral from 2 to 12 is 9. What is the integral from 7 to 12? Well, from 2 to 7 plus from 7 to 12 would give us the whole thing from 2 to 12. And I kind of just abbreviated that there. Every single one of these should have an f of x dx inside of it. But again, just, for the sake of time here, just writing it sort of abbreviated. It's kind of like part plus part equals the whole thing. So from 2 to 7, that's -5. Plus from 7 to 12 is what we're looking for. I'm just going to call that x. That's like the blank that we're looking for. Equals from 2 to 12 is 9. And so if you add over the 5, you're going to get 14 as your answer. All right, number 6, find the area under this graph from 4 to 7. So there's two ways you can do that. You can either do an integral from 4 to 7 and then do an antiderivative and then upper boundary minus lower boundary, or you can actually just draw it and find the area. I'm just going to draw it because I think that'll be a little bit simpler. So x minus 3, we're going to start at -3, and the slope is 1. So up 1 over 1, we want to go all the way out to 7 here. 1, 2, 3, 4, 5, 6, 7. And so here is our line. And so again, we want to go from 4 to 7. So the shape that we end up with is a trapezoid. And so trapezoid is 1/2 times the height. Now this is the height because it's on its side. So the height is 3. From 4 to 7 would be 3 units. And then you add the bases together. So this one is 1, and then this one is 4. And technically you don't need to simplify it down, so you can leave it just like that. 7, same kind of thing. Find the area between the x-axis and the graph of absolute value of x from -8 to +8. So here's absolute value of x. From -8 to +8, you get these two triangles, which are actually the same triangle because it's symmetric. A triangle is 1/2 base times height. So the base and the height would both be 8 units. So that would be 32. And we have 2 of them. So this one's worth 32, and then this one's worth 32. So your total answer for the whole thing would be 64. Or you could kind of think of it like if you flip this triangle over here, it would make a perfect square. 8 times 8 is 64. Either way, 64 is going to be your answer for that. Our number 8, find the average value of that function over the interval 0 to 8. So average, if I gave you a list of numbers and asked you to average them, you would add them all up and then divide by however much you've got. So the integral is what adds it up. And so out front, we're going to put 1 over 8 minus 0. And then this function, I'm going to write it as x to the 1/3. If we're going to have to do an antiderivative, it'll be better for it to be written that way. All right, so I've got that 1/8 out front, and then our antiderivative. We're going to add 1 to the power, so that will make that 4/3. And so I need the reciprocal 3/4 out front, and we're going to evaluate from 0 to 8. And then I'm going to kind of just clean that up a little bit. This would be 3 over 32. And then this is a cube root of x to the 4th. And you can put the 4th inside of there or outside. I think sometimes it's easier to cube root first and then take it to the 4th. Either way, you don't have to evaluate it unless if it's multiple choice. Upper boundary minus lower boundary, you don't really need to plug in the 0 because that would just be nothing. So essentially we're just going to plug in 8. Cube root of 8 is 2, and then 2 to the 4th is 16. And 16 over 32 would reduce to 1/2. So 3 over 2 is the simplified answer. Again, you would only need to do that if it was multiple choice. You could leave it as 3 over 32 and then cube root of 8 to the 4th. Just for the sake of this video and going through it with you, I'm just showing you how to simplify it down. All right, number 9, we've got a car slowing down as it approaches a red light. The car is still going forward. It still has positive velocity. Notice all these velocities are positive. The car isn't going backwards. It's just slowing down as it approaches the red light. So since it's slowing down, your velocity is decreasing. But it's still positive. It's still going forward. So approximate the distance traveled in these first 15 seconds using a right sum with these 5 sub-intervals. So the first sub-interval 0 to 2, that's 2. The number on the right is 40. And then the next one from 2 to 6 is 4. The number on the right is 28. 7 is 1, the number on the right is 19. 7 to 10 is 3, the number on the right is 11. And then 10 to 15 is 5, the number on the right is 5. And since that is a distance, it will just be feet. This is a velocity, feet per second, that's a rate. This is an approximate integral. So if you have velocity and you do an integral, you're going to go back to just position. So it's just feet. So is that answer an overestimate or an underestimate? All right, velocity is decreasing, so it's going downwards. And we did a right sum. So the right side is lower down, so it's going to be an underestimate because velocity is decreasing and this is a right sum. And then approximate, we're doing approximations for all these because we don't have an actual function to work with. It's just this table of values. Approximate the acceleration at time 12. So acceleration would be a derivative of velocity. I can't find a derivative because it's just a bunch of random numbers. So derivative means slope. We're going to do a slope to approximate that. T equals 12 would be in between here. So these are the 2 points that we're going to use, 10, 11 and 15, 5. And then we're just going to do the slope. And you don't need to simplify that down. But you do need to put units. This is feet per second. So an acceleration would be feet per second. So feet per second squared. It's a rate of change. All right, for all of these ones, I'm going to need scratch paper. This is where we're just going to integrate all these. Use all of your different methods of integration. All right, so for number 10, I'm going to let u equal the denominator. Du would be 2x dx, and then you go and look for that in the problem. I want it to be a 3x, so we're going to multiply this by 3/2. So the half cancels out the 2, and then I multiply by 3 to put the 3 in there. So we're going to replace 3x dx. Let me grab a highlighter. Hold on a second. All right, so we're going to replace the 3x dx with the 3/2 du. So 3/2 is going to go out front. Du goes at the end. What's still there is this statement in the denominator, which we let equal u. So 1 over u. And then that antiderivative is ln of u, which is x squared minus 2. And then plus c, because it's an indefinite integral. I don't have boundaries there. If there were boundaries, we would do upper boundary minus lower boundary, but since there's not, we don't have to do that. All right, number 11, we're going to let u equal this stuff inside. So the derivative of that would be 15x squared dx. I'm going to adjust it with a 1/15. So we've got x squared dx is what we're substituting for. In its place, we're going to put 1/15 du. So 1/15 goes out front, du goes at the end. What's left is u to the 6th. And then we're going to do the antiderivative, which would be 1/7 u to the 7th. And then again, plus c because it's an indefinite integral. And then you just have to replace u with this statement. So 1/15 times 1/7 5x cubed plus 8 to the 7th plus c. All right, so for number 12, we want to notice that we don't have anything in the numerator. So we're not going to be able to do a u substitution because if you let u equal anything in this denominator, when you do the derivative, that's not going to match up with what's in the problem. So this is going to be ultimately one of our inverse trig function patterns, but we need to complete the square in order to make it look that way. All right, so we're going to write down these first 2 terms, divide by 2 and square. So 6 divided by 2 is 3, squared is 9. And then I have to turn it back into a 13, so I'm going to add 4. And then the whole point of doing that is you can write this portion as something squared. So it'll be x minus 3 squared plus 4 in the denominator. And now it's going to follow one of our inverse trig patterns. I'm going to let u equal the x minus 3 part. The nice thing about that is the derivative is just 1, so du is dx. And then our a value is 2. 2 squared gives you 4. So if you want to do this step where you write out, this is going to be u squared plus a squared du, or if you just notice that that's going to be the inverse trig pattern, then you can kind of skip that part. Out front, we're going to have 1 over a, so that'll be 1/2 arctangent u over a, so x minus 3 over 2 plus c. All right, so 13 is going to be one of our inverse trig patterns. Actually, the same thing. It's going to be arctangent, but we don't have to complete the square. It's already sort of set up for us. U is going to be 6x. That squared would give us 36x squared. Du will be 6 dx, and we're going to adjust it with a 1/6. And then a is going to be 7. 7 squared will give us 49. So out front, we're going to have the 1/6 and then times 1 over a arctangent u over a, so 6x over 7 plus c. So we needed that 1/6 out front for the adjustment that we did right here. But then after that, it was just your arctangent pattern, 1 over a arctangent u over a plus c. All right, 14 is going to have to be split into 2 separate problems, one for the x and then one for the 7. If you try to just do it as a basic U substitution, it's not going to work out. So I'm going to split this into 2 separate problems. And I'm going to take that 7 and just write it out front. You can leave it in the numerator if you want, it doesn't make a difference. All right, and so we're going to do this as 2 separate problems, kind of like a part A and a part B problem. This one is going to be a basic U substitution. I'm going to let U equal the denominator. That derivative is 2x dx, and I will adjust it with a 1/2. It works out because you have the x dx in the problem that it'll match up with. So we'll have a 1/2 out front, du at the end, and what's left there is 1 over u. And so that antiderivative will be ln. So 1/2 ln of u, which is x squared plus 81. And I'm not going to put plus c yet. We're going to finish the other half of the problem and we'll put plus c at the end of the whole thing. This one's going to be your arctangent pattern. U is x, so du is dx, which is nice. There's not an adjustment there. A is 9. 9 squared gives you 81. And so this is going to be 7 out front times 1/9, 1 over a. So I'm just going to write that as 7/9 arctangent of u over a, so x over 9, and then we'll put plus c at the end of the whole thing. All right, 15, we're going to need to divide that out before we can do the integration, and I'm sorry. So 3 is the number that'll go in the little box off to the side. It's whatever makes the denominator 0, and then I'm going to steal all the coefficients from the problem. So 1, -2, 5, -1. You bring the first number down, and then it's multiply, add until you get to the end. So 3 times 1 is 3, add, you get 1. Again, 3 times 1 is 3, add, you get 8. And then 3 times 8 is 24, add, you're going to get 23. So when I put this back into the integral, it's going to be 1x squared plus 1x plus 8. And then this is your remainder. It just stays over that denominator. So 23 over x minus 3, and then dx at the end. So now we can do this as kind of like 4 separate terms to do the antiderivative. So this will be 1/3 x cubed plus 1/2 x squared plus 8x. And then this will be 23 ln x minus 3 plus c. It's technically a U substitution, but if you let U equal x minus 3, du is just going to be dx. There's no adjustment that needs to happen there, so you can kind of just go ahead and write it out as ln. All right, so looking at number 16 now. Now this one is a definite integral. So we're gonna not put a plus c, we'll do upper boundary minus lower boundary. And you can write out the U substitution if you want, but it's like I was just saying about this one with the x minus 3 with the x plus 3, it's just gonna be ln. If you let U equal this, du would just be dx. So there's no adjustment that needs to happen. So it's just gonna be 9 ln of x plus 3, and then we're going to evaluate from 8 to 12. So it's going to be upper boundary minus lower boundary. That would be 9 ln of 15 minus 9 ln of 11. All right, for this one, we're going to let U equal the stuff that is inside. So U is 1/5 x. du is 1/5 dx, and then we're going to multiply by a 5 to adjust that. So 5 will go out front, du will go at the end, and what's left is tangent of u. So this is one of the ones that you do just have to memorize. It will be negative, and then the 5 that's out front, ln of cosine of u, which is the 1/5 x, and then plus c. So it's negative ln of cosine, and probably just make some flashcards to go over those ones that you kind of just have to memorize. All right, number 18 is another one of our inverse trig patterns. This one's going to be arc secant. We're going to let u equal 4x. The derivative of that is 4, and then we'll adjust with a 1/4. And then a is going to be 7. 7 squared will give you 49. So the 1/4 is going to go out front, and then times 1 over a, so 1/7 arc secant of u over a. And this is the one that has the absolute value in it. I wouldn't take off for that, but it is technically there, so I'm just bringing it up, and then plus c. All right, 19 is another definite integral, so we will not put a plus c. We're going to actually evaluate this one. We're going to let u equal this stuff inside. So 4x squared plus 8. That derivative would be 8x dx, and we're going to adjust with a 1/8. So we're going to substitute for the x dx, and in its place, we're going to put the 1/8 du. So 1/8 goes out front, du goes at the end. What's still there is this square root of u, but it's in the denominator. So square root means that it would be u to the 1/2, but it's going to be negative 1/2 since it's in the denominator. And then we'll do the antiderivative. So you add 1 to the power. Negative 1/2 plus 1 will make it positive 1/2, which is good. That's not negative anymore. And then that reciprocal goes out front. And then we want to evaluate not from 0 to 3. We need to adjust those. So we're going to plug 0 in for x right here. That would give us 8. And then we're going to plug 3 in for x right here. So 3 squared will be 9 times 4 is 36 plus 8 will be 44. All right, so upper boundary minus lower boundary. 1/8 times 2, that would be 2/8 or 1/4. And then to the 1/2 power means square root. So it'd be square root of 44 minus 1/4 square root of 8. All right, number 20 is going to be another one of the inverse trig patterns. This one is arc sine. So we're going to let u equal the x plus 1. du is just dx. That's nice. There's no adjustment. A is going to be 8. 8 squared gives you 64. So arc sine does not have the fraction out front. That's the one that doesn't. So you will not need anything in front here. It's just going to be arc sine u over a plus c. All right, and then 21, we're going to let u equal the denominator. Derivative of tangent is secant squared. And so we're going to substitute for the secant squared of x dx. In its place, we're just going to put du. There's no adjustment that needed to happen. And what's still there is 1 over all of this, which is u. So 1 over u. And so that antiderivative is ln of u, which is that tangent of x minus 8, and then plus